Welcome back. In this presentation, we're going to discuss nuclear reactions and binding energy. We're going to use Einstein's equation, E equals mc squared, and try to explain why certain nuclear reactions happen. Think about what happens to the gravitational potential energy of an object Earth system when you bring the object closer to the Earth. That is to say, you're bringing together two things that are attracted to each other. Well, you're losing potential energy. Work is being done by the conservative force. And the same thing happens if you have two charges that are attracting each other, say a positive charge and a negative charge. If you allow them to come closer together, you're losing potential energy. Well, the same thing happens if you were to form a nucleus out of its constituent nucleons. Let's say you had two protons and two neutrons, and you brought them together to make a helium nucleus. Well, because if you get them close enough together, those nucleons are attracting each other. That means that they're giving up some potential energy. The potential energy they're giving up is called the binding energy. It is the energy not required to bind them together, but it is the energy that would be released when they are bound together. The bound together nucleus has less energy than the nucleons have individually. So this helps us understand why certain nuclear reactions happen. Let's say you have two deuterium atoms. That is to say, you have two nuclei that have a proton and a neutron each. Now, to separate those into their constituent nucleons, you would have to add energy to the system. But then, if you let them come back together again and they formed a helium nucleus, energy would be released. And if more energy is released than you had to add initially to get them to be separated, then this is a reaction that can occur spontaneously. This is a reaction that releases more energy than it takes in, and so it will happen. Now, the hard part, of course, is getting the two deuterium close enough together for that to happen, but if you do, it releases a large amount of energy. This is an example of nuclear fusion. So if the rearrangement of protons and neutrons results in a greater binding energy, then that reaction is going to release energy, and it's one that could occur spontaneously under the right conditions. You know, this binding energy we're talking about, the energy that gets released when these nucleons come together, well, energy is the same thing as mass, according to Einstein. And so it's also called the mass defect. If you have four nucleons, say here, and you were to carefully measure their rest mass, and then you were to allow them to come together, you would find that the mass of the combined nucleus would be less than the mass of the individual particles. And that makes sense if we keep Einstein's relationship in mind, because we just got finished saying they have less potential energy. And Einstein said energy is mass, and so if they have less energy, they should have less mass. This is called the mass defect, and it was the original way that Einstein's relationship was revealed to be true. So looking at binding energy gives us an idea of how stable a nucleus is going to be. Remember, the more energy it takes up to split it into its component pieces, the less likely it is going to be that it's going to split up into something. So something like iron, for example, which has the greatest binding energy per nucleon, is not going to split up at all. It's going to be very stable. Whereas something like uranium-238, as we see over here, has less binding energy per nucleon than iron, so it could split up into something smaller. We have to consider the binding energy per nucleon, because you may have a situation where overall a given atom has a large amount of binding energy, but that binding energy is kind of split up, if you will, amongst all of the nucleons that make it up. And so it could split up into two daughter nuclei, they call it, and the daughter nuclei may have greater binding energy per nucleon than the parent nucleus did, in which case the daughter nuclei would be more stable than the parent, even though the total amount of binding energy was greater in the parent nucleus. There are several different kinds of nuclear reactions possible. One of the most interesting ones, the most important ones perhaps, is nuclear fission. In nuclear fission, a parent nucleus splits up into two or more daughter nuclei. Here we see a neutron, that's a small little particle illustrated by the small circle on the top of this diagram, coming in and hitting a uranium-235 nucleus, turning it very, very briefly into uranium-236 nucleus. But the uranium-236 nucleus is very unstable, so it decays very quickly into a krypton-92 nucleus and a barium-141 nucleus, and releasing three other neutrons that can again go on farther and cause the reaction to continue. If that's what happens, then this is what we call a chain reaction, where one reaction releases neutrons, say, for example, that cause the reaction to happen again, and it just kind of continues in an ever-widening chain like that. A nuclear reactor uses a controlled chain reaction. It has materials inside of it that absorb the excess neutrons to make sure that it doesn't happen too much. Of course, in the first atomic bombs were uncontrolled chain reactions. They were fission bombs. Another kind of nuclear reaction that nuclei can undergo is called fusion, where just like the name sounds, the smaller nuclei come together and form a larger nucleus. Here you see an example of a deuterium, which is an isotope of hydrogen, and a tritium, another isotope of hydrogen, coming together and forming a helium and releasing a neutron. The binding energy per nucleon of the helium is higher than the binding energy per nucleon of the tritium or the deuterium, so therefore energy is going to be released in this reaction. In fact, this is the reaction that powers the sun, and it is also the type of reaction that we're trying to see if we could get to happen in order to release more energy than it uses. That's the big problem right now. We can get fusion reactions to happen, but because of the repulsion of protons with other protons, it's very difficult to get this reaction to start, because you got to get these protons energetic enough that they can collide together even though they're repelling each other. And that's hard to do. So you got to heat something up to a great temperature to get them to have a lot of kinetic energy, or you have to somehow compress them together in various ways. You can fire one nucleus at another nucleus and get this to happen, hopefully. The idea is to get past a break-even point where you can get more energy out of it than you put into it. But eventually we should be able to do this, at least we hope. So here's a question about binding energy. Correct statements about binding energy of a nucleus include which of the following? 1, it is the energy needed to separate the nucleus into its individual nucleons. 2, it is the energy liberated when the nucleus is formed from the original nucleons. Or 3, it is the energy equivalent of the apparent loss of mass of its nucleon constituents. So is it just A by itself, 1 by itself, or is it 3 by itself? Is it 1 and 2? Is it 2 and 3? Or is it 1, 2, and 3? Go ahead and pause the video and think about it, and then start it up again when you think you have the answer. It's actually going to be all the above. Each of these things is more or less saying the equivalent thing. When you take individual nucleons and bring them together, you're going to release energy. So that binding energy is the energy that gets released when you bring these nucleons together. It is how much energy you'd have to add again to separate them back into the individual nucleons. And as I said, it's sometimes called the mass defect. Because when a nuclear reaction occurs, it appears as a defect in the mass of the reactants and the products.